All right, hi everyone. Today we are going to review for the IA. So you will take that on Thursday. Since most of you do not take a Spanish class, you will take that on Thursday. So we're just going to do this very college style, just like we've done for the past year practically. Everything that we do is college based. So most reviews for midterms or finals or anything like that is just doing sample problems, and the professor just goes up to the board, does a bunch of example problems of things that are fair game for whatever assessment you're taking, and you all just take notes on it. And so that's what we're basically going to do here, just do a bunch of sample problems. So the first one here, we want to review our numerical methods. So we want to use backward Euler to approximate x of 2 for dx dt is equal to x, where x of 1 is equal to 1 and delta t is equal to 0.5. So if you remember sort of using our Python notation, I'm going to go ahead and do that, where we have x sub n plus 1 is equal to x sub n plus delta t times our function, where we have, I'm just looking at what I have on my notes, and I'm thinking I wrote my formula incorrectly. I think this should be x minus t. Apologize there. Okay, so then we have x of t, and then x of n minus 1, n plus 1 minus t of n plus 1. So inside our parentheses here, we put our original differential equation, and then since this is backward Euler, we have our implicit step here where we have n plus 1. So in backward Euler, if we remember, we need to get everything that is implicit on the left-hand side. So we're going to solve for our x of n plus 1. So let's go ahead and distribute our delta t. And then we can subtract over our x to the n, or n plus 1, or delta t term here. So x n plus 1 minus delta t x n plus 1 is equal to x of n minus delta t times t n plus 1. So I'm not subtracting over this term, or rather adding it over, because this is fine. I know what t of n plus 1 is going to be. It's just going to be my additional time step. So I don't need to subtract that over. So I can go ahead and factor out an x plus 1 here, or x n plus 1, excuse me. So I have 1 minus delta t times, this is not a subscript. That is my subscript. Okay, and now I just need to divide this term over, and now I have isolated my implicit term. Okay, so my first, I need to start with my initial condition. So x, my first here, so x of 1 is equal to 1. And now I need my time step, so x of 1.5 is going to be equal to, so my x of n, so my initial condition here, so x of 1 minus my delta t times t of n plus 1, so my current t is 1.5, divided by 1 minus 0.5. And if I crunch that out, that's going to give me 1/2. And so now x of 2, which is what I am trying to find here, is going to be equal to x of 1.5 minus 0.5 times 2 over 1 minus 0.5, and that's going to give me negative 1. So I've finished here, and my approximation for n, or x of 2 is equal to negative 1. All right, so my second example here, we're going to solve a differential equation using any of the steps or any of the types of solving methods we've used before. Okay, so we're going to stick with the similar function that we had before. Here we're just going to have y minus t. So looking at this, I see I have dy dt, so that is a first order derivative. So I'm not going to use any of these second order derivative methods. And I noticed that my y is not being multiplied by anything. So this is a linear function. So I have a linear function, first order, so but they're being subtracted. So I don't want to use separation of variables here because I know that separation of variables can only be applied when I have multiplication or division going on. So I don't want to do separation of variables. I could do a linear substitution here, so let's just write out our options. We could do a linear substitution because, like we said, this is a linear, they're being combined using multiplication or subtraction, so we could use linear substitution. We wouldn't want to use quotient substitution because there's no division going on. Our next method that we've talked about is our the exact functions. We never really named that fully, but we wouldn't want to use exactness here because we don't really have that format going on, that standard form. So we wouldn't want to use that. Integrating factors, well, this isn't in necessarily the integrating factor form, the normal form, but I could get it into normal form where I would have dy dt minus y is equal to negative t, where my g of x would be, well, g of t rather, but my g here would be negative 1, and my f would be negative t. So we could do that here. So it's all in your preference, whichever you prefer to do. So I prefer integrating factors, and I think a lot of you do too. So we could do this doing linear sub. So if you prefer to do linear sub, check your notes, look back on how we did that, and you can do that here. I'm just going to go ahead and do integrating factors. So integrating factors, so whichever you prefer, we're just going to do this one here. So I have this in my normal format. I subtracted over my y. So my g is whatever is attached to the y term here. So this is just going to be negative 1. And then my f is going to be everything on the right-hand side that is not a y term. So my f is going to be negative t. And so if you think back to integrating factors, we have our m, which is our integrating factor, is equal to e to the integral g, whatever your independent variable is here, so dt. So we have e to the integral of negative 1 dt, so that's just e to the negative t for m. And then we know that y, our whole function, is going to be equal to our f times the integral of m f here, and whatever your dependent variable is. So we know that this is our format here, so let's go ahead and just complete this. Sorry, I'm looking back at my notes, and I think that I have something incorrect here. So from here, we had the integral of m times f is equal to y times sorry, my notes are not following from what I'm remembering integrating factors to be. So I'm actually going to pause on this problem here. I apologize. We're going to come back to this because my notes are not matching up with what I remember integrating factors to be, and I don't want to tell you the wrong thing. So we're going to pause here because I don't want to give you the wrong thing. We're actually going to finish this in the Zoom call. So we're going to pause, meet me on the Zoom call later today to finish this problem. I apologize here. My notes are not following what I have integrating factors to be. So we're going to finish this one together. So before we waste any more time, let's just go ahead and do a different problem that will be more time friendly. So we want to solve y double prime plus 4y prime plus 8y equals 0. So here we see that we have a second order differential equation, and so that makes me think of all of my second order problems or solving methods that I know. So I could use roots, so my repeated, distinct, or complex roots. I could use my undetermined coefficients. I could use variation of parameters, order of reduction, any of those. Well, I see here that I do not have anything on the right-hand side that is a function. We just have 0. So this is a homogeneous equation. So I only want to use my roots here. So since this is a second order constant coefficient that is homogeneous, that differential equation, we want to use just our roots. So let's go ahead and sub in our r's. So I have y double prime, so that's going to be r squared plus 4r plus 8. Be careful here because I've seen this mistake way too many times. R squared corresponds to y double prime. So these two go together. Y prime, just highlight these. Y prime corresponds to r. Y does not get an r. It has nothing attached to it. So I've seen way too many times where I've had an equation where I have y double prime plus 4, let's not use 4 because 4 is in this equation, plus 6y. And a lot of you say, oh, well, that's just equal to r squared plus 6r. No, it's not, because y prime goes with r, y goes with r to the 0 power, essentially. So we do not want to make that mistake here, because that will severely change your roots. So now let's go ahead and just, we can do the quadratic formula for this, because I don't see a way to reverse FOIL this. So if I do the quadratic formula, I'll get r is equal to -2 plus or minus 2i. So I have a complex situation going on here. So remember that for complex roots, the first term is our a term, so that's going to be what's attached to the e in our exponent, and then the term that's being multiplied to the I, that is going to be our angle measure for our cosine and sine. So our solution here is going to be y is equal to c1 e to the -2t cosine of 2t plus c2 e to the -2t times sine of 2t. So again, this term here is what's going to go in the exponents. This term here, whatever's attached to the I, that's what's going to go inside our angle measure. So that's where our solution comes from. All right, so example number 4, we have 4x x to the third y to the third dx plus 3x to the fourth y squared dy is equal to 0. Okay, so looking at this, right away I think of exactness because our differentials are disattached from each other essentially, so it's not written as dy dx, this is dx times a term, dy times another term, so I automatically think to do my exactness test. So p is whatever's attached to my x and q is whatever's attached to y. So my p here is going to be, let's just write this, p of xy is equal to 4x cubed y cubed, and my q is equal to 3x to the fourth y squared. So when I'm doing my exactness test, I want to take the partial of p with respect to y. So my partial p partial y. So that means anything that is an x, I treat it like a constant. So I'm not going to derive any of my x terms here, but I will derive my y terms. So 4 is a constant, so that's going to stay. X cubed will be treated like a constant, so now I'm going to take the derivative of y cubed because that is my differential here. So I get 3y squared, so I have 4 times 3, so now I'm going to get 12 cubed y squared. And now my partial q partial x, so again I treat anything that is non-x like a constant. So I'm going to only derive my x term here, so 4x cubed. So this will give me 12x cubed y squared. So again, I treat y like a constant now because x is my variable of differentiation. So these two are the same, so I can conclude that these are exact. So now, the beautiful thing about this, I can just integrate p and q separately and combine what is the same and different about them. So let's go ahead and just integrate these. So if I integrate 4x to the third times y to the third with respect to x. So now the original differential here, this is going to be again, I only am going to integrate anything that has an x, anything that is a y, I'm going to treat like a constant. So if I integrate x cubed, that is going to give me x to the fourth over 4. So if I have x to the fourth over 4, and now I have this constant here, those are going to cancel out. So I'm just going to leave this as x to the fourth times y cubed, because again, this is essentially a constant, and then my plus c of y. So I could have some sort of function of y here that is not present, that was left behind. And now if I integrate q with respect to y, I have the integral of 3x to the fourth y squared dy. And so if I integrate y squared, I'll get y cubed over 3. So again, I have the same phenomenon going on where my 3 is going to cancel out with the integral of my y term. So I'm going to just be left with x to the fourth y to the third plus c of x. So we can see these are exactly the same, so that just means that my constants are actually 0. So my final solution here, my f, is going to be equal to just my x to the fourth y to the third. And that is all of that is going to be. All right, so our fifth example here, we have y double prime minus 8y prime plus 16y equals 0. So again, I have a second order differential equation that with constant coefficients that is homogeneous. So again, I'm going to use my roots here. So r squared minus 8r plus 16 is equal to 0. If I reverse FOIL this, I'll see I get r is equal to 4 with a multiplicity of 2. So this is a repeated root. So that just means I need to attach a t to my second term. So I'm just going to get c1 is equal to e to the 4t plus C2 is plus C2 T e to the 4t. And that's all that example is. Okay, so example number 6. I'm going to have y double prime minus y is equal to x. So here, again, I need, this is a second order differential equation with constant coefficients, but now we are non-homogeneous. So I'm going to have to either use undetermined coefficients or variation of parameters. Here I'm going to use undetermined coefficients. I could use variation of parameters, and we will do that in a later example. So from here, I have r squared minus 1. Again, so y does not get an r term. So we're just going to take the homogeneous portion of this. So a lot of you on your IA set this equal to x. That is not what the roots method is for. That is for finding the homogeneous solution. Then the undetermined coefficient portion will find the non-homogeneous portion of your solution. So we get r is equal to plus or minus 1. And so now my homogeneous, so y of h, is equal to c1 e to the x, since we are using x here, plus c2 e to the negative x. And so now I need to use my guesses. So this is undetermined coefficient, so we guess the particular here, so y sub p. And that is based on whatever our function is over here. So since this is just a linear term, I'm going to guess a linear function. So let's just have ax plus b as our guess. And we have a second derivative here, so I need to find the second derivative of my particular. So y prime of p is equal to is just a, actually. And then my y double prime is just going to be 0. So now I set this up, my guesses here, into the same format as my original differential equation. So I have 0 minus ax plus b, and that is equal to x. And so here, again, we sort of have that phenomenon going on where we want to match up what is the same. So the only term on the left-hand side that has an x is this negative a. So we have negative a, x is equal to x. And then all of my constants are going to be paired up. So 0 minus b is equal to 0. So that means that a is going to be equal to negative 1. So if I solve for a here, I get negative 1. And if I solve for b, I'm going to get 0. So that means my particular here, I sub back in what I know. So I have negative 1x plus 0. So I'm subbing back into my original y of p. So that's just going to be y of p is equal to negative x. So when I put these all together, I have my y is equal to yh plus yp. So this is for undetermined coefficients. So that means that y is going to be equal to c1 e to the negative, c1 e to the x plus c2 e to the negative x minus x. And that is our general solution using undetermined coefficients. Okay, so we know that when we're making guesses, sometimes we have to adjust. So let's look at an example where we have to adjust our guess so that we know when to do that. So in this example here, we did not need to adjust our guess because this term, our ax plus b, was not similar to anything inside our homogeneous solution. So we were good to go there. But sometimes we need to do that. So for our seventh example here, y double prime minus y is equal to e to the x. So this first half here we already did in the last example, so we can just go ahead and write our homogeneous solution to this. So c1 e to the x plus c2 e to the negative x. And so for our yp, we need to make a guess based on our forcing term or our function on the right-hand side. So our yp, based on our what we put in our notes, if this is e to the x, then we would guess a e to the x. However, you notice that this term here could be this term here, and we don't want that. So we need to adjust our guess. So we need to adjust, and we basically do that just by adding a t. So this would be yp is equal to a, well, since we're dealing with x's instead of t's, we just add an x. So ax e to the x. If this were to be a repeated root situation, we would have to adjust again, because if this was a repeated root, then we would have c2x e to the x, and then that would be the same here. So if I were to, if I needed to adjust again, then I would just have x squared. So I just keep incrementing that power there. But I don't need to do that here, so we're fine with this. So again, I have a double prime, so I need to find my yp double prime. So my first prime here, we need to use our power rule. So we have, or excuse me, our product rule, since we have a variable times a function of a variable. So a e to the x first, the last plus last do first. I did this out of order, but you get the picture. That is our product rule. So our double prime here, we have to do product rule again. So we get a e to the x plus a e to the x plus a x e to the x. So this simplifies to 2a e to the x plus a x e to the x. So now I need to take my particulars here and make it look like my original function. So I have 2a e to the x plus a x e to the x minus my first p here, so y, my first y, and then that's going to give me e to the x. So we can see that these two terms are going to cancel out, so I'm left with 2a e to the x is equal to e to the x. So solving for a here, I get a is equal to 1/2. So my particular solution is going to be yp is equal to 1/2 x e to the x. So my final solution, we know we combined our homogeneous and our particular, so we get c1 e to the x plus c2 e to the negative x plus 1/2 x e to the x. And that is our solution. All right, so our final example that we're going to do is going to be for a variation of parameters. So this is going to be when we have y, so example 8, so y double prime plus y is equal to secant x. So here we have again this non-homogeneous because we have this portion, so that's why we're going to do variation of parameters. But we have this constant coefficients with a second order differential, so we could use undetermined coefficients or variation of parameter, but I'm just going to use variation of parameter since the last two we did were undetermined coefficients. So we have r squared plus 1 is equal to 0. So this is going to give us r is equal to plus or minus I. So then for variation of parameters, we need a y1 and a y2, which is basically just our RH, but we split up the terms. So we have cosine of x. Since we have no a, we're not going to have an e to the a t. That's not going to exist. And then since the constant being multiplied to the I is 1. We just have 1 times x inside our angle measure. So those are our two. So from undetermined coefficients, we need to find our Wronskian. I apologize. I keep saying undetermined coefficients. Variation of parameters. Let me just write this so I don't keep saying this wrong thing. So for variation parameters, we need to find our Wronskian, which is basically a derivative. So this is going to be our y1 times y2 prime minus y2 times y1 prime. So this is going to be cosine times the derivative of sine, which is just cosine, minus y2, so sine, times the derivative of y1, so negative sine. So we know that this is just going to be equal to 1 cosine squared plus, since this is a negative times a negative, plus sine squared is just going to be 1, so our Wronskian is 1. That is a happy day when that happens. So now we need to find our u's. So u1 is going to be equal to the integral of negative y2 times our function over our Wronskian. So here negative sine of x times secant of x over 1, and the integral of that dx. So here secant is 1 over cosine. So if I rewrite this as sine over cosine, this is the integral of tangent, which is just equal to the natural log of cosine plus c1. So I didn't really need to rewrite this as tangent, because if I look at this, I could do a u sub where u is equal to cosine, and then I would have 1 over u du, and then we know that that's the natural log, so I would just have the natural log of cosine. So that's where this comes from. A lot of you missed that on the quarter 2 IA. Even though we did that together in class, you need to know that the integral of tangent is the natural log of cosine. Do not forget that. So our u2 is going to be the integral of y1 f of x over our Wronskian. So here we would have cosine times secant of x over our Wronskian, which is just 1. So again, happy day when that happens. Dx. And so this one is not as... Oh, well, no. This one is even nicer than the first one. So because secant is 1 over cosine, we would just have cosine over cosine. So that's just equal to the integral of 1, which is just x plus c2 in this case. So our final solution here, so our y is equal to u1 y1 plus u2 y2. So our y1 was cosine, so we have our u1, which was the natural log of cosine, plus c1, that whole quantity. A lot of you forgot your constants after you integrated, and that made you mess up your solution in the end. So you have to be careful here. Do not forget the constant. So this times cosine of x plus x plus c2 times sine of x. And then that is our solution here. I can go ahead and distribute. It really doesn't matter, but we can go ahead and just do that. So c1 cosine of x plus the natural log of cosine of x times cosine of x plus c2 sine of x plus x sine of x. So you can see here we have this homogeneous portion here. It's what we thought it was before, c1 cosine plus c2 cosine. And then this is comes from our variation of parameters. So this is our y of p, essentially, if we would have done undetermined coefficients here. Okay, so in our Zoom call, we have some problems to work on for the classwork for today, so please join the Zoom call. We'll go over example number 2 for integrating factors that we did not finish here, and then we will have a Q&A for anything on the classwork or anything that we went over just now. All right, have a great rest of your day, everyone.